Continue on here, chapter 17. And we're getting into electrochemistry. And we started talking about redox reactions last time. Again, redox basically stands for obviously oxidation and reduction. And remember that oxidation basically means that something has lost some electrons. Reduction means that something has gained electrons. And those are two of the definitions that we commonly use here in general chemistry. We also talked about gaining oxygen or losing hydrogen as two other definitions of oxidation, or gaining hydrogen and losing oxygen, which is also two definitions of reduction. Those you typically see a little bit more in organic chemistry than you do in general chemistry. So here we kind of look at the electrons. We also talked about the oxidizing agent and the reducing agent. And remember that they're basically opposite of their names. So the oxidizing agent is the substance that gets reduced, while the reducing agent is the substance that gets oxidized. And again, as we talked about last time, those are different questions. Again, if you're asked, what is being oxidized versus what is the oxidizing agent. So again, they are different. All of those things, the substance that is being oxidized or reduced, or the oxidizing agent and reducing agent, are always found on the left-hand side of the arrow. So there always should be reactants. You could look at the oxidation state, or number, to determine what is going on. And some rules, right? Oxygen is usually a good place to start. It's -2. Things that are in their kind of natural state uncombined are 0 in terms of their oxidation state. Hydrogen is usually +1 and so forth. So you could use the oxidation states. And as we talked about last time, a reminder that oxidation number, oxidation states are not always the sort of charge you have maybe in your head of these certain elements. The charge you have in your head is probably the charge it is if it's an ionic compound. But when these elements, for example, something like we talked about chlorine last time as well, when chlorine, for example, shares electrons with other elements, it can, in some cases, take on a more positive charge or oxidation state based on the difference in electronegativity of whoever is sharing electrons with. You could also, if you're not sure, just use a basic number line to figure out what is going on in terms of oxidation and reduction. Again, when things lose electrons, they become more positive because they have more protons than electrons. So if you look at the oxidation state from the left-hand side of the arrow to the right-hand side of the arrow, and it's moving in this positive direction, then that guy is going through oxidation. If you are looking at an oxidation state and it's becoming more negative, and that happens when things gain electrons because they now have more electrons than they do protons, and they would be moving in terms of their oxidation state in this direction, the more negative direction, then that guy is going through reduction. So that's just the basic way. Just draw an arrow and see which way it's pointing, and it'll tell you basically if it's being oxidized or reduced. We have half reactions where if we have electrons on the product side, that is like they're being given off or lost, and that is your oxidation half reaction, where we should always have those guys over here. Your reduction half reaction, where they're being gained, they actually should be on the reactant side, and that would be your reduction half reaction. Again, they're called half reactions because basically if you add both of those together, you get the overall reaction back. Remember that before you could add these guys back together, the number of electrons in each half reaction does need to be the same number so that they completely cancel out. If they are not the same number in one or both, obviously, of the half reactions, then you need to get them to the same number. So that may require you to multiply maybe one half reaction by a number, may require you to multiply both half reactions by a common number to get the number of electrons that are the same. I think that's sort of where we laid up. Any questions on any of that there? Redox, as you also we talked about last time, is the broad category of reactions. that involve a transfer of electrons, and you may be familiar again with more specific sort of classifications of those reactions. These are all the reactions like synthesis reactions, decomposition reactions, single replacement reactions, and combustion reactions. These are all basically examples of redox reactions that take place. Double displacement reactions are not redox reactions. Acid-base reactions, which are double displacement reactions, are not redox reactions, nor are precipitation reactions redox reactions in most cases. All right, so then let's talk about the steps to balancing a redox reaction in acidic or basic conditions. And again, we're just going to kind of go over this, make sure everybody's on the same page before we get into really the true part of the chapter. But when we're trying to balance a redox reaction in either acidic or basic conditions, there's a few more steps involved in terms of balancing the redox reactions, rather than just trying to make sure we have just the right number of electrons in each half reaction. So the first thing you want to do is split off your equation into the two half reactions. So you should have an oxidation half reaction and a reduction half reaction. So you should have your two sort of half reactions there happening. So one should be an oxidation, one should be a reduction half reaction. Then the next thing that you want to do is, and by the way, to do that, it's a pretty simple process. You just pick the two things on opposite sides of the arrow that have the same elements in them, right? So we got Mn on the left and Mn on the right. Pick those two and put them together. You got a chromium on the left and something with chromium on the right. Put those two together. So just pick the ones that have the same elements, basically, and put them together. Once you do that, we're going to actually balance the equation. We're going to balance all elements except hydrogen and oxygen. And how we're going to do that is just like a normal, you're going to balance an equation. You're going to use coefficients to do that. So you're just going to put the proper coefficients in front, just like you're balancing a normal equation. Once you've split off your two half reactions, once you've balanced out everybody besides hydrogen and oxygen, you're actually now ready to balance out oxygen. And we then would balance oxygen. And the way that we balance oxygen in this sort of process is we actually use water to balance oxygen. Now, what we do is whichever side of the half reaction needs oxygen, we put the appropriate number of waters there to balance out the oxygens. Now, as you know, obviously from the formula of water, we're not really just adding to that side oxygen, but we're also adding hydrogen. And to keep yourself from becoming unbalanced when you do that, for every water you add to one side, to the other side, you need to add 2 H pluses. So for every water that you put on one side, you got to add 2 H pluses to the other side. What that's going to do is basically balance out your hydrogens to make sure you got the right amount of hydrogens on each side. By the way, there could be a situation where maybe you just start out with, for example, let's just say you had this, and maybe you just had like this to start out with. And obviously we're unbalanced in terms of the hydrogen to start with, for sure. So you could always just add an H plus to the other side. Excuse me. Thank you. To balance out the hydrogens to begin with. At some point, you'll need to add an H plus to balance out that hydrogen. And you could just do that up front, and it'll all kind of balance together. Once you've done that, and now that you've balanced the oxygens and you balance the hydrogens, what you need to do next is actually balance out the overall charge in each half reaction. And the way that we do that is we actually use electrons to do that. So you're going to add the negatively charged electrons, obviously, to whichever side of those half reactions needs a negative charge. Now, when we do this, what we're looking for is not for each side to equal 0 necessarily. We're looking for each side to have the exact same charge. So if one side is 0, you want to make sure the other side ends up at 0. If one side's like +3, then you want to make sure the other side ends up at +3 or -6, -6. So it doesn't have to be 0 on both sides, but it does need to be the exact same charge on each side. And again, since we're only adding electrons to do that, you got to put it to whichever side needs it. Now, I personally, and as I'll show you in just a second, I personally just look at the overall charges of everybody. Sometimes people are taught like to look at each individual element and see what's happening. That's a waste of time because as we know from our oxidation states, the overall charge of the molecule or ion is equal to all the oxidation states added together. So what I mean by that, for example, is if I was doing something with this guy, I'm not going to go and try to figure out again what nitrogen's oxidation state or oxygen's is. I know when it's all said and done, overall it's a -1. So that's all I have to think about in terms, okay, that's a -1 on this guy. That's a +1 on this guy. That gives me a 0 charge overall on this guy. So that's just the quickest way to do it rather than kind of go element by element. It kind of does the math for you because the overall charge of the compound should add up from all the oxidation states. Once you've done that, you want to make sure you have the same number of electrons in each half reaction. And again, if you do not, then you may need to multiply, right, by a common number. So the goal here is we're actually ready to kind of add these back together. And what you want to do is make sure in each half reaction you have the same number of electrons. Again, if you don't, it may require you to multiply one half reaction by a number or both. Once you've done that, you're going to then add both half reactions together. The thing that should cancel out for sure is the electrons. So the electrons should completely cancel out. When you add those reactions together, anything on opposite sides of the arrow that are the same can either completely cancel out or reduce down. So reduce down or cancel out. But the one thing that should always completely cancel out are electrons. So electrons should always completely cancel out. By the way, as we'll talk about when you get to this part where you're adding the electrons, you should never add electrons to the same side. Otherwise, they're not going to cancel out and you did it incorrectly. If you do all that successfully, you will be balanced in acidic conditions. Yeah. Now, to go to basic conditions, you're basically the easiest move is basically just follow all those steps again. So just follow it like you're going to balance it in acidic conditions. And when you're done, you will have an equation that may have some H plus in it. And to balance it in basic conditions, you're going to add OH minus to both sides. The amount of OH minus you're going to add is equal to the amount of H plus that you have. So we had 4 in this little example here. We would add 4 OH minuses to the left and also 4 OH minuses to the right. The side where there's OH and H plus, they will combine and make water. And in a lot of cases at that point, you'll be able to kind of reduce down the number of waters on both sides because you'll have some waters on both sides. And if you do all that, you will then be balanced in basic conditions. And that probably is the easiest way to do basic conditions. You could actually do basic conditions way back, like in this step, but it does have a lot more stuff you got to cancel out along the way. It's just a little bit cleaner to wait to the end and just kind of turn it to basic at the end, but you can do it before if you wanted to as well. You just have like I said, a lot more stuff in the inner part of your calculation there or problem to cancel. Any questions on that? All right, that's a lot of words. Let's go through one here together again, show you. Hopefully, maybe you did this or not. I don't know. But we will make sure we know how to do it. So let's say we wanted to balance this guy here in acidic conditions. And by the way, the notes are up there, so they should be up on Canvas now. What we're going to do is I personally like to first kind of think about what's going on in terms of what's being oxidized and what's being reduced. So if we do that, this guy here is, I think I might just rewrite it up on top there. Give me a little bit more room, I think. Fe2 plus Cr2O7 2 minus, and Fe3 plus, and chromium. All right. I did that. Free up a little bit more room, I think. Oh, too much room. All right, so let's take a look at this one. The oxidation state here of anything that's really a ion by itself is its charge. So this guy is +2. We actually did dichromate on the very last example, I think, that we finished up on last time. And a reminder, this is -2, gives it a -14, equals -2. There's 2 of those. That's a +6 happening there for the chromium. This would be +3 for this iron, and the chromium here would be +3. So again, if you want to figure it out using kind of the number line approach here, our iron is actually starting at +2, and it's ending at +3, which means it's moving in the positive direction. And that means that this guy is going through oxidation. Remember, if you can successfully do one of those or figure out one of those, by default, this guy is going to do the opposite thing here. But we could also do it for the chromium. Chromium started at +6, and it's ending at +3, which means it's moving in the negative direction and going through reduction. So again, that's the way you can figure it out. That would also mean in this particular case that the iron here is my reducing agent, as that is the guy being oxidized, and it's my chromium here, really, or the dichromate, if you want to take the whole thing, is my oxidizing agent. First off, any questions on the oxidation numbers or identifying what's being oxidized or reduced? All right, then let's take a look at what we should do next. First thing we're going to do is just split it off into its 2 half reactions. So clearly the iron should go together and the chromium should go together. And again, as we identified, that's my oxidation half reaction, and that is my reduction half reaction. All right, we are now ready to start our balancing. So now that we've split it off, we're going to do our balancing everybody but hydrogen and oxygen. And in this case, we have 1 iron on each side, so we're good. On the bottom, we have 2 chromiums on the left, but only 1 on the right. So we do need to put a 2 there in front of it, just like we're balancing a normal equation. Now that we've balanced every element but oxygen and hydrogen, we're actually ready to get to oxygen. There is no oxygen in the top half reaction, which means we don't have to worry about it. Bottom half reaction, there are 7 oxygens there and none on the right-hand side. That means on the right-hand side, we would need to add 7 waters. Again, that is what's going to balance out our oxygens. Because we added the water, which has hydrogen, that means to the other side, we do need to add 14 hydrogens. That again is what's going to balance out our hydrogens that we just put on the other side. All right, so we've now balanced oxygen and hydrogen. The next thing that we're ready to do is actually add electrons. So again, here, I personally like to look at overall charge on each side. So this guy has a +2 charge. This guy has a +3 charge. That means that the negative electrons needs to be added in this case to the right-hand side, and we would need 1 electron. That 1 electron is going to contribute a -1, and that's going to give me +3 and -1, which is +2 on the right to match the +2 on the left. So again, does not have to equal 0 on both sides, but the same charge overall. Looking at the bottom, this is what I was saying before. I'm just going to go about overall charge on everybody. So this is going to contribute a +14. I don't really care about individually everybody in there. I know overall, this guy's at -2 charge, and that's going to yield me a +12 happening on the left. On the right-hand side, that is 2 times 3, which is +6. And that is 7 times 0, which is 0. So that is a +6 yielded over there on the right-hand side. In this case, we do need to add electrons to the left-hand side. And we would need to add, in this case, 6 electrons. That's going to give me a -6, and a +12 gives me a +6 on the left to match the +6 on the right. Any questions on that there? All right, now that I've done that, I'm actually ready to add these together. But before we could add it together, we do need to look at the electrons in each of these half reactions, because remember, the electrons do need to cancel out. And in this case, we do not have the same number of electrons, right, in each half reaction. By the way, before we do that, we also know that we added the electrons to the correct sides, because this is an oxidation half reaction, which means electrons should be added on the right. This is a reduction half reaction, which means electrons should be added on the left. So again, if you're adding them to the same side, you screwed up. Yeah, so they should never add to the same side. So since we do not have the same number of electrons in each half reaction, you do need to multiply, in this case, the top guy by 6, again, to give us the same number. So I'm just going to rewrite it underneath everything, I think. Just going to do that. So multiplying that 6 across the entire reaction gives me 6 Fe2 pluses, goes to 6 Fe3 pluses, and 6 electrons. The bottom guy we're not going to do anything with, so I'm just going to recopy it so we can kind of look at it here together. And now we're ready to add these guys together. Again, as usual, the electrons should always cancel out. Again, anything on opposite sides of the arrow that's the same can either completely cancel or reduce down. In this case, I think that's everything that's going to cancel. So everybody on the left-hand side stays there, and everybody on the right-hand side of the arrow stays there. So that's going to give us basically 14 H pluses, plus a Cr2O72 minus, plus 6 iron 2s, gives me 6 of the iron 3, plus 2 of the Cr3 plus, and 7 waters. If I did not mess anything up here, I should be balanced in acidic conditions. We could check that very easily by, frankly, just making sure it is balanced. And when we talk about balancing and the thing disappears right at the wrong time, right? And totally disappears at really the wrong time there. Ouch. All right. Let me just borrow. Maybe I have one pre-worked out, I think. There it is, maybe. Yep, there it is. We'll just steal this one here. I guess I'll start rewrite it here. All right. All right, so this is our balanced equation that we just got, I hope. And again, we can look at it and make sure it's balanced in 2 ways. It has to be balanced like a normal equation, which means when you add up all the elements on each side of the arrow, it needs to be the same. So here we have 14 hydrogens on the left, and on the right we have 7 times 2 is 14. Chromiums, we have 2 on the left and 2 on the right. Oxygens on the left, we have 7 and 7 on the right. And iron, we have 6 on the left and 6 on the right. So it's balanced like a normal reaction in terms of elements on each side. It also has to be balanced in terms of its charge. And again, if we look at this here, that's a plus 14. That is a minus 2. And that is a plus 12. So that's like plus 26 less 2 is a plus 24 charge on the left. That is a plus 18. That is a plus 6, and that is still a 0. So 18 and 6 is plus 24. So it is balanced in both ways, and that is what it always should be when you have a redox reaction. It should always be balanced with the elements and also the charges as well. Questions on that one there? All right, so let's talk about then what to do if we want basics. So as I mentioned before, if you want basic conditions, I would just do everything we just did and balance it in acidic conditions. And at the end, you can turn it into basic conditions. By the way, I know this is acidic conditions because I see H plus, yeah. So because I see H plus there, I know I have balanced it in acidic conditions. I can now, again, at this point, turn it into basic conditions. And if I do that, I'm going to add 14 OH minuses, which is equal to the amount of H pluses I have to both sides. And again, this side where we added it, where there's the H plus and OH minus, will combine to make 14 waters. At this point, you could reduce down the waters. There's 7 on that side. That then would become 7 waters plus our Cr2O72 minus plus R6 and R3 there, our couple chromiums on this side, and our 14 OH minuses. This then would be balanced in basic conditions. And just like that, I turned it into basic conditions. By the way, I know it's basic conditions because in this equation, I don't see H plus, but I do see OH minus. So again, I know it's basic conditions in this case. And it should still be balanced when you do that. So again, we have 14 hydrogens there, we got 14 over there. We got 7 oxygens there, and 7 more is 14 oxygens, 14 oxygens over there. We got 2 chromiums on the left, 2 on the right, 6 irons on the left, and 6 irons on the right. So we're balanced. Overall charge now on the left-hand side, that guy's contributing 0. This guy's contributing -2. This guy's contributing +12. That's a +10 on the left-hand side. This guy is contributing +18, +6, and -14. So that is basically 6 and 4 is 10. So you again are balanced both in charge and also elements. Any questions on that there? All right, so why don't you try one just to make sure everybody knows. Do they still teach this in Chem 50? They do? No? Oh, okay. Yeah. Depends on your teacher, I suppose, maybe. I suppose, yeah, no, yes. All right, so we'll do, why don't you give it a go, make sure, yeah. Okay, let's take a look and see how you're doing here. So again, we'll just start with what's going on. And this guy's oxidation state is -1. -2 for the oxygen here gives you a -8. Overall, it's -1, which means that's a +7 for the Mn. I2 is naturally how it comes, so that's a 0. -2 for the oxygen over here, -4, and a +4 there for our Mn. So in this case, again, we can look at each of them. In terms of the I minus, is starting at -1 and ending at 0. It's moving in the positive direction, which means it's going through oxidation. By default, that would mean the Mn here is being reduced. We could also see that with the Mn. Mn is starting at +7, which is over here, ending at +4, which is moving in the negative direction. So it is being reduced. This would mean that the I minus here is our reducing agent, and this guy here would be our oxidizing agent in this case. Once we sort of have that all sorted out, we will split it off just element to elements that go together. So the I's together and the MNs together as well. Going to balance everybody but oxygen and hydrogen. So we do need a 2 there for the iodide. We then, that's everybody. I think Mn on both sides, we have 1. Now we're ready to add oxygen. So the other one that has oxygen is the bottom half reaction. And again, this is our oxidation half reaction, our reduction half reaction. We will need to add 2 waters here to the right. And because we added 2 waters to the right, we need to add those 4 hydrogens to the left. Again, otherwise we're going to be short. Now we are ready to balance with electrons. So overall charge here is -2, and this is 0. That means we need a couple of electrons here to get us to basically -2 on both sides. Bottom, that is +4. That overall thing is -1, so that's a +3 happening. Right-hand side, that's a 0, and that's a 0. So that means in this case, we would need to add 3 electrons over here. That's going to give me a -3 and a +3, which will then take me to 0 on each side. Yeah. Any questions on that? Yeah. At this point, we are ready to add these guys back together. But before we do that, we got to look at our electrons. And in this case, we do have different numbers of electrons. Common number between those guys is 6, which means the top guy needs to be multiplied by 3. The bottom guy needs to be multiplied by 2. So I'm going to rewrite them underneath, but first I can get rid of some of those numbers. So I have a little bit more room here to kind of do it there. So I'm just going to kind of get rid of those guys. All right, so rewriting each of those ones and multiplying, it's going to give me 6 I minuses, goes to 3 I2s and 6 electrons. On the bottom, 6 electrons plus 8 H pluses plus 2 MnO4 minuses goes to 2 MnO2 plus 4 waters in this case. At this point, we're now definitely ready to add. And once again, we can verify that we did add correct electrons, oxidation, product side, reduction, again, reactant side. So that's all good as well. Electrons should completely cancel here. And I think in this case, it is going to be everything that was canceled. So everybody on the left stays there. So 8 H pluses, 2 MnO4 minuses, and 6 I minuses. Goes to 3 I2 plus 2 MnO2 and 4 waters. If we wanted acidic, we would be done in acidic in this case, right? And everything is balanced. We have 8 hydrogens on both sides, 2 Mns. We got 8 oxygens on each side, and we also have 6 iodines on each side. Overall charge on the left-hand side is 0. And overall charge on the right-hand side is 0. So again, it's balanced the two ways it needs to be balanced, and it is balanced in acidic conditions. Once again, I know it's acidic conditions because I see the H plus in there. In this case, though, we did want basic. So what we're going to do now is turn it into a basic equation, and we're going to add 8 OH minuses. We're adding 8 because of the H pluses we have to each side. Excuse me, happy face. There we go. We'll go over there. These guys are going to combine to make 8 waters, which usually in this case means you could then reduce down some waters because you usually will have some on the other side. And that will get me a grand total of 4 waters on the left, plus 2 MnO4 minus, plus 6 I minus, goes to 3 I2 plus 2 MnO2 and 8 OH minus. And at this point, this should be balanced in basic conditions. Again, should still be balanced the two different ways. We have 8 hydrogens on the left and 8 on the right. 4 oxygens on the left and 8 more is 12. 4 oxygens and 8 more on the right is 12. 2 Mns on both sides and 6 Is. Overall charge on the left is -8. Overall charge on the right is -8. So again, it's balanced in both ways, like a normal equation and overall charge. And once again, I know it's basic now because I see OH minus in my actual equation. Any questions on that there? Going to try one more just to make sure. Let's try. Yeah, let's do this one. Balance this one in acidic conditions. Also figure out obviously what's being oxidized. Here, the dichromate, we've done this guy a couple of times. That's a +6 happening, a -2 there for the oxygen. Here, that's a -2, that's a -8 equals -2. There's 2 carbons in that case. These equal +6, I think, in this case. So each of them are +3, I believe. Chromium here is +3, and -2 there, -4, +4 in this case. So once again, we can see that the chromium here is starting at +6 and it's ending at +3, which means it's moving in the negative direction. So this guy is being reduced. By default, this guy is being oxidized, and we see that with the carbon at +3, ending at +4, and again, becoming more positive in that case. That means our oxidizing agent is our dichromate, our reducing agent there is our oxalate in this case. We're going to split them off here, so chromiums with chromiums. And carbons with carbons in this case. Yeah. Go this way. And this is my oxidation. This is my reduction half reaction. All right, starting with everything other than oxygen, we do need a 2 here for the chromiums, and we actually need a 2 here for the carbon as well. We now will go to our oxygen, and we will need to add 7 waters to the right-hand side. That's going to give us 14 H pluses to the left. On the bottom, by actually putting the coefficient in front of the CO2, we actually balance the oxygen as well. So there's now 4 on each side. So we actually don't need to add any waters to the bottom one in this particular case. Now we're actually ready to add electrons. So again, overall charge here, +14 and a -2, that's a +12 happening. Right-hand side, that's a +6 and a 0, which means +6 and 12. That means 6 electrons over here. Gonna get me a +6 left over there now. And that's balanced. Also put it on the correct side as that's my reduction half reaction. So I put it on the left-hand side there where my reactants are. Overall charge here, got a -2 and a 0. So a couple of electrons here should take care of this guy. And that is good because that's my oxidation half reaction. So I added it to the correct side in this case. Any questions up to that point? Now we need to get our electrons in order, and we can just simply, in this case, multiply the bottom guy by 3. So I'm just going to rewrite everything below. So we'll do both of them again here. And then multiplying that 3 to the bottom guy. Now ready to add electrons again, completely canceling. And again, I think that is it. So we'll go 14 H pluses, Cr2O72 minus, and 3C2O42 minus. Goes to 2 Cr3 plus and 7 waters and 6 CO2s. And if I didn't screw anything up, we should be balanced again both ways. I got 14 hydrogens on the left and right. I got 2 CRs on each side. I got a grand total of a lot of oxygen, but I think that's 19 on the left and also 19 on the right, and 6 carbons on each side. Overall charge on the left, that's going to contribute a +14. That's going to contribute a -2 and a -6. So that looks like a +6 on the left-hand side. That is a +6 on the right, and 0 and 0. So we are good in both ways that it needs to be balanced. Once again, we do again know it's acidic conditions because there is our H plus, right? So we see our H plus here, and we know it's balanced in acidic conditions. Any question on how to balance these redox reactions? Yeah. So that's the thing you always want to keep in mind when you're doing any type of redox reactions, be it an overall reaction like this, or just looking at half reactions. You always want to make sure it's balanced on both sides, and it should be balanced always in that kind of 2 ways, like a normal equation with elements, and also the charge should always be balanced on both sides of the arrow. All right, so now that was maybe somewhat of a review or new stuff. I'm not sure, depending on your situation. But let's get into really what we want to talk about here in this chapter, which is galvanic cells. And this is a picture of a galvanic cell. that you could build in the laboratory. And a galvanic cell has several parts to it. But ultimately, what a galvanic cell is, it's just a big old redox reaction happening. So we have these electrons that are being transferred. On the left-hand side here in this picture, this is the anode side, and the anode side is where oxidation occurs. And we have a solid electrode, in this case zinc, and we have a solution that contains zinc ions, positive ions floating around. It also has like sulfate in this example, but the sulfate's actually just like a spectator ion hanging out, not much going on there. The zinc is going to go through oxidation, which you can see on the bottom there means the zinc's going to go from solid to zinc with a 2+ charge, and it's going to give off a couple of electrons. It's going from 0 to +2, once again on our number line there, going from 0 to +2, moving in the positive direction, becoming oxidized in this case. When zinc loses its electrons, it goes from the solid state and decides to jump into the swimming pool. Yeah. And it jumps into the swimming pool as aqueous ions as it loses those electrons. Those electrons then travel across a wire, giving you some voltage. Those electrons can be used to do some type of work, like when you put a battery in something, right? There's wires, electrons go out and power your device. And it goes to the other side of the galvanic cell, which is a cathode side. And at the cathode side, that is where reduction occurs. And what you have on this side of this cell is a copper solid electrode, and you have a solution that contains copper ions in it. So what happens is as these electrons come in, they drop down into the solution and hook up there with the copper and reduce it. And the copper decides, I've swam enough, I'm going to go out of the pool and become a solid, basically. Yeah. You got one guy diving into the pool on the left, the other guy getting out of the pool. He swam too long. And that is what is happening in this particular case as those electrons basically transfer over here to the other side. By the way, this half reaction is balanced, got one copper on each side. Overall charge on the left is 0, and overall charge on the right is 0 as well. Again, the copper going from, as you can see here, +2 to 0, moving in the negative direction, again, becoming reduced. There is also a salt bridge that is here. The salt bridge connects both of the compartments of a galvanic cell. It has a pretty important sort of function, as we'll talk about here in just a second. It's usually filled with some type of electrolyte solution, some type of salt, like in this case, potassium chloride is what's in there. It's got some cotton plugs so the salt bridge doesn't fall out on one side or the other. The salt bridge is really important for keeping the cell moving and keeping the electrons moving. There is already what is sometimes referred to as a potential difference between the anode side and the cathode side. You could think of it as the cathode side is more positive. It's going to drag the electrons, which are negatively charged, to the other side, right? That's what makes it kind of want to go that way. Opposites attract each other. So the salt bridge allows for the galvanic cell to continue to function without a buildup of bad charge on each side of the cell. So what do I mean by that? I mean by that if you took this cell here, I'll just kind of draw the beakers underneath them. And let's just say that we removed the salt bridge and we let the cell run. What's going to happen is obviously our electrons are going to travel, right? And they're traveling in this direction. Now, if we took the salt bridge out and this reaction continued to run, what's happening on the anode side is our guy's going for a swim into the pool, which means we're really adding to this a bunch of positive charges, right? And what's happening on the right-hand side is this guy is getting out of the pool, and that's really leaving only the negative counter ion in this side, right? And you're going to get a buildup of a bunch of negative charge over here if you took the salt bridge out. That's problematic because electrons are negatively charged, which means they're going to want to stay over here because now this is way more positive, right? So they're not going to want to move to the other side. In addition, this side's more negative as you take the salt bridge out. So that's going to prevent them from going that way either. And that's going to stop the flow of electrons from going from the anode to the cathode. That is why when you look at the salt bridge in the original picture, it is dumping here the chloride to this side, right? Which is negatively charged. As it dumps that chloride in there, it's going to combat that buildup of positive charge over here and keep it where it needs to be. That's also why the potassium, which is positively charged, is heading over to this side. And that's going to kind of bring back some of that positive charge to that side that we're losing as those guys leave the solution. So the salt bridge functions to keep the charges on each side of the galvanic cell from building up in the wrong direction. And that would ultimately stop the flow of electrons. And ultimately that would stop your cell from making voltage, right? Which is kind of the purpose of it, right? Is to make some voltage that can be used to do some type of work. Any question on the salt bridge? How that works. This is a spontaneous reactions. If we add these two half reactions together, like they did over there, we got our zinc going to our zinc 2 plus and our 2 electrons. The 2 electrons are going to come on over to the copper and go to our solid copper really here and our aqueous guy. We add these guys together, the 2 electrons cancel, and we do get the overall reaction that we see there on the bottom, which is overall what is happening. Our zinc is going from 0 to +2 being oxidized. Our copper is going from +2 to 0 being reduced. This is happening because our zinc is sending those electrons over. And because this guy is being oxidized, in this case, our zinc is our reducing agent because it's causing the reduction of copper. And the copper is our oxidizing agent because it's causing the zinc to lose those electrons, right? So again, that is what's happening in this particular case. Any questions on a galvanic cell, the build there of it? Yeah. So here is a picture kind of that cell there, and you can see if you hook up your electrodes there to your galvanic cell, if you kind of zoom in, that is the salt bridge right about there. As you can see, kind of connects both of them together. And again, we get some positive voltage happening here, which, as we'll talk about, is actually a good thing. You usually want positive voltage, not so much negative voltage. And there's that potential difference, as I mentioned before. You kind of think of like the cathode side being a little bit more positive. It's going to help kind of pull those electrons to the other side. You are sometimes asked to calculate the cell voltage in this situation, and a volt is equal to 1 joule over a coulomb. You're also sometimes referred to calculating the electromotive force, or the EMF, or the cell potential. Those are essentially, if you're asked to calculate any of those things, they're basically asking you to calculate the voltage of the cell is basically what they're looking for. There is also another way that sometimes galvanic cells are displayed, and that is what is referred to as the cell diagram. And the cell diagram looks something like this, and on the bottom here. And it's always written in this sort of orientation: anode on the left, cathode on the right. This is basically your anode compartment, and this is basically your cathode compartment. These two lines here represent the salt bridge. So how do we go, for example, from the cell diagram to an equation? The basic formula for how that happens is this. This is usually a reactant, that's usually a product, that's usually a reactant, and that's usually a product. So as you can see, zinc reactant, zinc product, copper 2 reactant, copper solid product. So that is usually kind of the order as to how you kind of pull it from a cell diagram into an equation. Now, there are also sometimes things that you will see in the cell diagram. For example, this one also has, for our ions, which is where we find ions, which is in the solution, it has the concentrations. And in this case, it's 1 molar, which is standard conditions. Again, a reminder, standard conditions, 1 molar, 1 atmosphere. Not all sort of anodes or cathodes are solids, some are gases. And for the ones that are gases, they typically will use some type of inert solid uh, element or solid substance as the actual physical electrode. So something like a platinum wire, something like graphite is used sometimes in place of a physical one because really it's a gas and there's not like a physical representation like there is, say, you could grab a piece of iron metal or a piece of copper metal. You can't really grab a piece of hydrogen metal because there isn't one. So, they use something that's really chemically inert but acts as a solid electrode that they could hook really the wire to and allow those electrons to kind of come to the other side. Now, for example, here, if we hook this cell up as an example of that, here we have our zinc as our anode. So again, this solid zinc is going to go off and make zinc 2. Electrons are going to come over in this case, and this is hydrochloric acid, which means there's H pluses in that solution. So as the electrons come in, it's going to reduce this guy to our bubbly hydrogen gas. Yeah, that's going to happen in this case. And again, because hydrogen doesn't really have a physical electrode, in this case, they're using platinum as like the physical sort of electrode to put in there for your galvanic cell. And that's what we see here. This again, anode and cathode side here. And once again, our overall reaction, we have our reactant and our product, our reactant and our product here. So again, that is how we get to it. We can see zinc is getting oxidized, going from 0 to +2. In this case, the hydrogen from the acid going from +1 to 0, getting reduced in this particular case. And you can see in this cell diagram, they have the atmospheres because we're dealing with a gas. And they also have listed the platinum as like this sort of solid electrode in there. Because the platinum is the electrode, it's listed in the cell diagram, it doesn't make its way to the overall reaction. It's just kind of put in there to let you know sort of what is being used as a solid. Now, speaking of this, how do we know, for example, what is the value of all these elements in these reactions? There is, as we will see, what is referred to as a standard reduction potential table, or sometimes abbreviated as an SRP table. And standard reduction potential is basically all reduction reactions. So this table that we will see is basically all reduction reactions, which means, frankly, one of the reactions in there is incorrect based on a redox reaction because we need an oxidation reaction to occur. But how we get all these SRP values that we're going to see in this table is that they decided to use the hydrogen electrode as the standard electrode to compare everybody with. And they call that the standard hydrogen electrode, or sometimes abbreviated as the SHE for standard hydrogen electrode. They sort of arbitrarily gave it a value of 0 volts and basically used that to compare everybody else to. And this again is a reduction half reaction because electrons are on the reactant side. And again, it's our hydrogen going from +1 to 0, again being reduced in this case. So basically how they got all these values that we see in this table eventually here is they took the standard hydrogen electrode and basically hooked it up with other elements and ran basically a galvanic cell. So for example, if they hook the zinc up here with our standard hydrogen electrode, they get a cell voltage of 0.76 volts for this cell. And they could use this equation here, which I'm going to tell you something about in just a second. That probably won't make sense yet, but eventually it hopefully will. And this is the cell potential that you could calculate. And this is E of the cells equal to E of our cathode minus E of our anode. And in this particular case, the zinc is our anode, and this is our cathode. And since the cathode is 0, and the cell gave us 0.76 volts, and the cathode, which is our standard, is 0 volts minus our anode, bringing that negative to the other side, that's how we know E of our zinc. in this case, is going to equal minus 0.76 volts. And again, you can see this reaction is written as a reduction reaction, which they all are. That equation you can use to calculate the cell voltage. And if you are going to use this equation, you should use it with the values you find in that table the way they are. And that's why they have a subtraction. So what I mean by that is in this particular case, if you went to this table, this is what you would see. You would find the zinc, and it would look just like this reaction we have on the bottom. And it will have an E naught of minus 0.76 volts. And if we hooked it up, obviously, with our hydrogen there, and our hydrogen half reaction, as we saw here on the previous slide, I believe, right there, is our H plus going to our H2. So we have our 2 electrons plus our 2 H pluses going to our H2, and our E naught is equal to 0. So in this situation, this is our anode, and this is our cathode. Anode is where oxidation occurs. Now, technically speaking, this reaction, as it's written, is a reduction reaction. If I wanted to write the oxidation reaction, which is really what is happening in this reaction, or this sort of galvanic cell, I would have to reverse that reaction, and it would actually be the zinc going to my zinc with a 2 plus and my 2 electrons. Because I reversed a reaction, technically speaking, the E value for that reaction will now have a different sign. It will actually be positive 0.76 volts. Then when I add it to my other reaction here, which is my hydrogen one, I will get this, and my E naught for that guy there is 0 volts. That means when I add it together, the electrons will cancel out correctly. It will give us our overall reaction that's actually taking place, just like we did with our other redox reaction. Now, because I switched the sign and I gave the value that really truly goes with the oxidation reaction, I actually need to add those numbers together to get the E of the cell. So what I would do is take 0.76, the positive version of it, plus 0 volts gives me 0.76 volts for the cell voltage. So if you decide, which is perfectly fine to do, that you want to change the sign for the oxidation one, which is always the anode one, and that will always be the one that you should change the sign for, you actually need to not subtract these two values. You need to add the two values. So if you change the sign, you should add these together. Now, if all you care about is, I want the cell voltage for this cell that I built, and I don't really care about writing the equation or anything like that, or if you don't want to have to change the sign, what you could do is use this equation here and not change the sign, and go to your table and go, my E of my cells, my cathode, which from my table is 0, minus my anode. And again, I'm not going to change the sign, and do minus 0.76 volts, going to give you plus 0.76 volts, just like we got on the bottom. The reason this is a minus is it will change the sign for you for what you find in the table. So if you just want the equation to change the sign for you for your anode, you should take the value you find in the table exactly the way it is with the incorrect sign, and that minus will change it to the correct sign and do the calculation for you. So if you don't want to change the sign, you should subtract. Yeah. I would highly recommend that you probably choose one way and stick with it. Yeah. Because you do not want to change the sign and then subtract because you just undid it. I saw people do that like yesterday, actually. They were like, I don't know, I get the wrong answer because like they changed the sign, then they subtracted it, which changed it back. So you got to make sure that you pick one way and do it. They're both perfectly fine. I personally do the subtraction one, no matter what the situation is. So I just know when I go to the table, all I have to do is just find the two things, right? And then find which one's the anode, which one's the cathode, stick it into the equation, it'll change the sign for you. But technically speaking, the correct way, for example, though, if you were going to write this half reaction, this technically is the correct E value for how it's written. And if you want to change it, you should add it, but it's really your call. But again, like I said, I would probably choose one way and stick with it. All right, we laid up there